Hello and welcome to our presentation. Thank you for taking the time to hear about what our group has been working on for the past several months. We're going to talk about green infrastructure solutions to our campus flooding in Urbana, Illinois. My name is Xin Teng, and the rest of my group members who are presenting today are Ryan Moeller, Abhijit Saraf, and Justin Shen. We're going to talk about the flooding issue at the veterinary medicine facility at the University of Illinois at Urbana-Champaign. This facility currently houses the veterinary teaching department, clinic, and laboratory. This is one of the fastest growing departments in the university, and it is crucial for us to be part of the effort beautifying the entrance of the facility. If you look over at the picture on the right side, the south parking lot highlighted in blue is the main entrance, where prospective students who would enter from Lincoln Avenue and get their first glance of the facility. The north parking lot is highlighted in orange and located right next to the academic building, which is bordered with orange marker. On this slide, the picture shows the drainage routes for the veterinary medicine facility. Currently, the stormwater collected on the north parking lot drains in the direction of blue arrows shown in the diagram to the blue circle, which is an area adjacent to the south parking lot. The stormwater collected on the south parking lot enters the manholes and follows the black arrows that travels across Hazelwood Drive. Here are some of the problems this facility faces during high rain events. Stormwater floods the dairy farm across from Hazelwood Drive. The runoff leaches the nutrients in the soil at the dairy farm. So our project aims to reduce the stormwater runoff and beautify the entrance of this facility by incorporating green infrastructures. Now my teammate Abhijit will elaborate on the design portion.
Thank you, Sisi. For the purpose of assessing reduction in the runoff at the facility due to our design solutions, we consider two design rainfall parameters. The first is the 95th percentile rainfall. In accordance with the EISA Act, a federal facility needs to develop measures to retain 100% volume of rainfall due to a 95th percentile event. The 95th percentile event is that amount of rainfall which is higher than the rainfall received in 95% of all events based on historical records. Historical data was retrieved for Urbana, Illinois, and this data was plotted, and the value was calculated to be 2.18 inches per day. Secondly, in accordance with standard texts such as New York Stormwater Management Design Manual, 24-hour 5-year events are used to assess the overall reduction in runoff volume. From NOAA, this value was noted as 3.73 inches per hour. Next, please. As CC mentioned earlier, our design goal is to reduce the stormwater runoff at the facility. For this, we consider two design solutions. The first is the installation of a rain garden in the green area adjacent to the south parking lot, which would capture the runoff from north parking lot and its surrounding areas. The second solution is the redevelopment of south parking lot by the introduction of bioretention swales. Now Ryan would walk you over the rain garden overview.
Thanks, Abhijit. Our proposed rain garden will retain runoff during storm events and is designed to prevent rapid flow across Hazelwood Drive. Two areas were considered called the north area and the green area for our efforts. The north green area being the area to the east of the north parking lot, and the south green area being depicted by a blue circle to the west of the south parking lot. Ultimately, only the south green area was considered because only one storm drain flows to the north parking lot, while the rest of the north parking lot and the surrounding green areas flow directly to the south parking lot and then across Hazelwood Drive. The image on the left shows three different design options listed as A, B, and C that we chose to evaluate both volume reduction for water and cost reduction. The university's first rain garden, the Red Oak Rain Garden, was developed and finished last year, roughly a mile north of this site through the Illinois Climate Action Plan, and we expect this project would likely see similar support. Next, I'll explain the design of our rain garden. This slide shows a cross-section of our rain garden design, which would require about 3 feet of excavation for the different rain garden designs across the whole surface area. The smallest design would require roughly 500 cubic yards of excavation, while the largest of the designs would have just over 1,000 cubic yards. If soil tests show that the soil in the area is uncontaminated, we could keep it on site for reuse. The silty clay loam in the area, according to soil samples, has a drainage of roughly 14 inches per day, which is adequate for a rain garden, which requires between 12 and 24 inches per day. The image on the right shows a cross-section of our under-drain system, which has a 6-inch perforated PVC pipe to allow for extra drainage in rapid flow events. Here we have a depiction of our runoff and volume reduction, as well as the 3 options listed again on the right. Our EPA SWMM calculations showed that during a 95th percentile event, roughly 30,000 cubic feet of stormwater would flow in over a 24-hour period. While that exceeds the storage capacity of our designs, we could achieve over 75% reduction with our largest design and just under 75 with option B. Additionally, the existing slopes in the area allow for more than 6 inches of ponding, which was our design shown on the previous slide. To meet design requirements of 100% reduction, we could either increase ponding on options B or C to 12 inches, which would match the existing slopes, or we could expand the rain garden to the area directly north of the sidewalk in that southern green area. Here we have the 3 options again shown on the left, mostly to help visualize the different surface areas. Our goal moving forward would be to work with faculty and students in our landscape architecture department to find an aesthetically pleasing design that better fits the existing contours, essentially to avoid having a square rain garden. Unfortunately, that process fell through in the spring when classes moved online, but it would be the next logical step moving forward. Now Abhijit will give an overview of our parking lot redevelopment.
Thank you, Ryan. Our second design solution pertains to the redevelopment of the south parking lot. The south parking lot forms the main entrance to the facility and has a surface area of nearly 2.5 acres and a catchment of nearly 3 acres. Next, please. For modeling purposes, EPA SWMM has been used to assess the runoff reduction in the post-development scenario. The drainage plan of the existing parking lot was retrieved from the Facilities and Services Department of the university. The main features of the EPA SWMM window consists of subcatchments, manholes, conduits, and rain gauges. The 2 design rainfalls mentioned earlier are designed as second quartile events. Next, please. To accurately model the parking lot, the elevations of manhole junctions were determined using level survey and site investigation, and this also aided in the delineation of subcatchments. The areas and slopes of subcatchments and the length of conduits were determined using Google Earth. Next, please. Now Justin will run you over the parking lot redevelopment plan.
As Abhijit previously mentioned, the south parking lot currently consists of many subcatchments due to elevation differences around the lot. Parking medians in general would be the optimal locations for BMP implementation, but the highest elevations of the lot are situated currently at the medians. Due to this, our design includes a redevelopment of the parking lot so that our BMPs are located at the lowest points in the lot while still being situated at the median. This allows for efficient stormwater routing that minimizes water in the drive lanes while also maximizing retention. Here we can see a basic bird's eye view of the parking lot drawn within AutoCAD. Our design consists of 8 bioretention swales of varying sizes with a perforated PVC piping system that drains to the storm sewer below. The parking spaces are on the north and south sides of each swale, while the manhole covers are denoted with squares with crosses. In terms of parking, we will see a 48 spot decrease, which is calculated to not be an issue according to common parking lot requirements. Now, the above image shows our proposed swale sections overlaid onto an image of the existing parking lot. As stated before, there are 8 overall swales, but some swales contain different sections, which are denoted by the different colors. This is again because of the various subcatchments in the lot. For example, water falling within the section labeled 1 will route to a different manhole than water falling within section 2. The bottom image is a bird's eye view of the swale made up from sections 1 and 2. The small vertical markings represent the tops of the perforated piping system. These are spaced unevenly because the differing areas of section 1 and 2 must be accounted for, thereby ensuring that the retention of each subsection will be evenly distributed. This design approach is applied to all of the swales within the parking lot. And now I will discuss the dimensions of our swales. This image shows a cross-section of our swales. There will be a 6-inch ponding layer on top, followed by a 3-inch mulch layer, then 36 inches of planting soil, and then an 8-inch gravel layer that has a sloping bottom. The 6-inch diameter perforated pipe will be located in the middle of the gravel layer, an inch from both the top and the bottom. Now Abhijit will further discuss EPA SWMM for our swales.
Thank you, Justin. The bioretention swales were designed on the EPA SWMM window using the LID controls provision. The sizing of different components in the bioretention swale was done in accordance with standard texts such as Georgia Stormwater Management Manual. Next. Upon running the simulations, we find that the runoff out of the swale sections for a 95th percentile event was 0 for all sections, and the overall reduction in runoff volume for a 24-hour period for a 24-hour 5-year event was nearly 2%, or a total of 200,000 gallons. Next, Justin will run you through cost estimates.
We computed our preliminary cost estimates using a limited version of 2011 RS means due to a lack of access to newer versions. We inflated our obtained values to 2020 costs, but however, there are some missing components still. This estimate should be considered on a scale for evaluating the different options. Now, rain garden option C is the most expensive rain garden design, but it offers the most detention capacity at just under 24,000 cubic feet. On the other hand, the parking lot redevelopment will be much more expensive than the rain garden construction and maintenance, and also offers less detention capacity than 2 of the rain garden designs. But it's still necessary to combat flooding of the parking lot. Next, I'll discuss our decision matrix. Our matrix is sorted by 4 decision factors, which are detention capabilities, cost, difficulty of implementation, and aesthetics, with detention capabilities having the most weight and aesthetics having the least. The lower the score, the better the option. All in all, rain garden option C has the best score of the 3 rain gardens. This result falls in line with the goal of our project, since option C provides the most detention capacity at a negligible increase in cost compared to the next best option. Now, Ryan will summarize our project.
Our primary objective with this project was to mitigate runoff from the veterinary medicine facility across Hazelwood Drive to prevent it from leaching runoff from the student farms to the south. To reiterate, our project aimed to reduce flooding in 2 important areas: the culvert leading under Hazelwood Drive to the dairy farms and the storm sewer that also empties on the farm properties. Because the culvert and storm sewer are separate, there must be 2 solutions to address both systems. Our primary strategies for combating the issues are a rain garden in the green area to provide storage, as well as bioswales in the parking lot to reduce flow and peak events. Based on our decision matrix, the most effective solutions would be rain garden option C, which, as Justin said, had the highest detention capacity, as well as the parking lot redevelopment plan with bioswales. Both options were more costly, but ultimately our simulations showed they would have excellent detention capacity in our target 95th percentile events. And the university has shown similar support for similar green infrastructure improvements in recent years. Next, we have some additional considerations for our project.
Thank you, Ryan. This slide shows some additional considerations: soil tests, a stormwater pollution prevention plan, and soil composition and drainage. Soil tests are necessary to determine if contaminant concentration would prevent on-site reuse. A stormwater pollution prevention plan would be put in place to ensure mitigation of soil runoff in the event of rain during construction. It would include silt fencing and vegetation of any stored earth. Ideally, we would need to check soil composition and drainage during the environmental testing phase for the whole project to work. We would like to acknowledge the following professors, faculties, and engineers on the slide who have helped us along with the project. The other members of our team are Jinglin, Bennett, Lindsay, Ashna, and Nathan. And thank you for listening.